Hello. Hi. On this another dreary afternoon. Okay, all right. So let's get started because I have a lot of stuff to do today. Reminders, homework 2 is due tonight. Lab 3, a demo is not due till next Tuesday. However, really you should be aiming to be done at the end of tomorrow because Murphy's Law says that something will go wrong and you want to give yourself enough time to figure out what's wrong. Right? You don't want to arrive next Tuesday and realize, oh, this won't work. Okay. Any questions before we get started? No questions. No questions out there. Really, no questions? Okay. All right. In that case, we shall proceed. Okay. So on PowerPoint. Okay. So on Monday, we talked more about flip-flops and building counters with flip-flops, and we had a simulation of a simple circuit with 2 flip-flops, and we did one, and there is actually a second one here to do. So let's do this one. So as you recall, the way these work is that the flip-flops will load whatever value is on their D input at the clock edge. The clock edge here is indicated by the dashed line. The dotted line is when the flip-flop output will assume its new value. So even though the value is loaded at the dashed line or sampled at the dashed line, the flip-flop doesn't change to the new value until the dotted line. Okay, and this is what lets us put a bunch of flip-flops in series and have each one capture the value of the previous one. All right. So in almost all of these, you will be told that the flip-flops are uninitialized. This, of course, is not the case for your designs. On the FPGAs, all the flip-flops are reset to 0 at the beginning for you, so that's nice. And you can actually reset them all to 0 using the global reset. Okay, but in this diagram, we are specifically told the flip-flops are not initialized. So if we have to fill in the timing diagrams for these things, well, the first thing we probably want to do is get equations for the D inputs here. So we're going to label the D inputs. So D0 will be the input for the flip-flop holding Q0. And its logic equation is, well, D0 is the XOR of X and Q1. D1 is the input of the flip-flop that holds Q1, and D1 is an OR, a plain OR of Q0 and X. And Z here is an OR as well. It's the OR of Q0 and not Q1. So unlike the one we did on Monday, here Z doesn't depend on the input directly. So it's a little bit easier in the sense that we only need to know Q1 and Q0, and Q1 and Q0 change right at the clock edges, so Z will just change a little bit after the clock edges as a result. Okay, so what are they before the first clock edge? What are Q1 and Q0 before the first clock edge? Unknowns. All right, we have no idea. We're going to put red X's just like the simulator. All right, so at the first clock edge, what happens with Q0? X is 1, and Q1 is unknown, so what gets loaded into the Q0 flip-flop? Nothing gets, something always gets loaded, but unknown gets loaded. Some unknown value gets loaded. In fact, whatever Q1 had, inverted actually. Okay, but it's still unknown because we don't know what Q1. The XOR, you don't know the value of the XOR unless you know both of the arguments. Okay, that's not true for an X. It's possible to know the OR, the value of an OR, if one of the arguments is a 1. Right? But for an XOR, you need to know both. So until we know both Q1 and X, we're not going to know D0. Okay. What about Q1 here? What happens with Q1? Anybody? Yes? Okay. Because X is 1, D1 will be high regardless of Q0, and so we will load a 1. And Q1 will go to 1. Okay. All right. Next clock edge, what happens with Q0? Yes? Goes to 0 because Q1 is now 1, X is 1, 1 XORed with 1 is 0. Okay. What happens to Q1? It's still high. Okay. All right. At this point, I don't have to worry about unknowns anymore because both my flip-flops have known values, and the X is known, so there's no way I can get an unknown now. Okay. What happens to Q0, next clock edge? Zero? How many people think it's 0? X is high. What's Q1? So it's still 0, right? 1 XOR 0. 1 XOR 1 is 0. Okay, Q1? So high. Oh, I'm 1 ahead. Okay. Q0, what happens with Q0 now? Well, not yet, but so X is still 1 and Q1 is still 1, so Q0 is still 0. Q1, what happens to Q1? Well, X is 1, so it stays 1. Okay, so it kind of revealed itself. What happens at the next clock edge? Now it goes high because X is low, but Q1 is still high. So we have a 1 XOR 0, which is 1. Okay, what happens to Q1? Goes low. Okay. Okay, what happens now to Q0? Zero. All right, so how many of you following this? Uh-oh. All right, so we're using these equations, right? These are the inputs to the D flip-flops, and so to figure out what Q0 will be after the clock edge, I need to know what D0 is right now. And D0 is Q1, which is 0, XORed with X, which is 0. So I have 0 XORed with 0, that's D0. So at the clock edge, that will be loaded, and then Q0 will become 0. Okay, so this is just plugging in for D0 and D1 based on the values right at the clock edge, and that's the value that Q0 and Q1 will assume after the clock edge. Okay, so what happens with Q1? It goes high because Q0 was high. Okay. All right, now Q1 is high and X is low, so Q0 goes high. And D1 will go low because X is low and Q0 is low. Okay. All right, so you guys get to fill these in. Any questions on this? Yes.
Depending on how the circuit is set up, these will be kind of like standardized, right? Like they'll behave the same way if it's the same circuit.
What do you mean?
If you, there'll be kind of like an expected pattern if you know what, if you set up your circuit the way you want to, right? Like if you have the same hookups and the same two flip-flops, it'll
Yeah.
always have the same pattern.
Well, assuming I feed it the same X, yes.
Yeah. So is that part of like what you're looking for when you're building circuits, is like an established pattern?
Well, it depends on what function you want to implement. There are a variety of different things that we want to build, and how we build that circuit we will certainly discuss. But right now, the purpose of these simulations to make sure you understand how these flip-flops work and understand what you'll see in the timing diagram, because what you see for Q0 and Q1 are the values that were based on the values that were present before the clock edge, not the current values. Okay, so we still need to do Z. So for Z, we're going to look at the immediate values of Q0 and Q1. Okay, we don't need to look at the D0s or D1s. Z is just the OR of Q0 and not Q1. Okay, so do we know it in the first clock cycle? No, they're both unknown. We're not going to know it. How about here? Do we know it in the second clock cycle? Yes? No? Okay. Well, what is Q1? It's 1, but we have Q1 bar. So this is 0, ORed with unknown. So that's still going to be unknown. Right? If it were just Q0 or Q1, then it would be 1, but it's Q0 or not Q1. Okay, how about the next clock cycle? What? Now it's 0, okay, and this didn't change, and this didn't change, so I can just fill those in again. Okay, how about the next one? Okay, Q0 is 1, so we know it's 1. Okay, the next one, 0, 1, 1, 0, 1. It's an OR, right? No, it's not an AND. Okay, any questions on these? Yes?
Maybe I'm not reading it right, but on the cycle that it finally registers that there's a
Value?
Yeah, value. Isn't the previous value also, there's like an unknown amount?
Yes, Q0 was unknown until here. But now Q0 is known and Q1 are known, and we can plug them in and get the values for Z.
But I mean, like, but Z would know immediately?
Yeah, Z reacts immediately to changes in, Q1 or Q0, or very quickly on this scale.
Oh, okay, yeah, that makes
That's
sense.
the difference here. Z is a combinational function of Q0 and Q1. It does not depend on the clock. Okay. Q0 and Q1 are outputs of flip-flops. They will only change as a result of a clock edge. Right? So you see Q1 and Q0 only changing on the dotted line, and the value they assume are based on what D1 and D0 were at the dashed line. Okay. So this is what you're going to see when you run the simulator. Okay. And it's going to look like the distance between the dashed and the dotted line is going to be very, very small. In fact, you won't be able to, you'll wonder, okay? And only when you zoom in to the picosecond level will you see that it's actually changed 1 picosecond after the clock. Okay, so you have to remember that they actually change value after the clock. Okay, all right. I will assume, any questions on this before I move on? No. Okay, so last week we started talking about K-maps and coming up with minimal sum of products expressions. And we'd never talked about product of sums. And so now I'm going to go back and talk about product of sums and how we do those. For the homework tonight, you're only doing sum of products. Okay, you don't have to worry about product of sums. The next homework, homework 3, you'll get to do product of sums as well. And don't cares. Okay, so just to recap, since it's been a week, remember we talked about coming up with minimal sum of products expressions because we wanted our logic to be small as possible. And we measured our, did you have a question? No? No? You didn't have a question? Okay. A literal in a Boolean expression is the occurrence of a variable or the complement of a variable in an expression. And that's how we measured our sum of products. We want to minimize the number of literals in our expressions. An implicant is a product term that covers only values or elements of the function's onsets. So it's only 1 when we want our function to be 1. It may not be 1 for every possible 1 we need, but at least it's not going to be 1 when we want our function to be 0. So we can use an implicant as a product term in our sum of products. Okay, and so we did an example. This is the example we did. When we have the K-map, it's easy to find these implicants because we can draw rectangles that only cover the 1s. The important thing is that these rectangles cannot have dimension 3. They can only be 1 by 2 by 4 by 8, whatever, but only powers of 2. Okay, so we have a bunch of rectangles I can draw that only cover the 1s. I can draw 4 1x1s, and these would actually correspond to the minterms for that cell. The product term for cell 6 is ABC bar, which is the minterm 6. Okay. But I can draw some bigger rectangles, some 2x1s, right? I can draw this 2x1, corresponds to the product term AB. This one is BC bar. This one is AC. Remember, we talked about how we figure out the product terms. We have to know whether the rectangle is in part of the K-map where the variable is 1 or in 0, or if it straddles the 2 areas. Okay. All right, so these are all the implicants. However, we only care about the prime ones. Never should you ever draw an implicant that's not prime. Okay, an implicant is prime if it cannot be made bigger. If making it bigger would cover a 0. Okay, so all of those minterms were not prime because they were inside 2x1s. Okay, so never ever draw an implicant that's not prime. We only need to use the prime ones. If you were to include a non-prime implicant in your sum of products, we could replace it with the prime implicants it's inside and it would have fewer literals. So there's never ever a case where you're going to want to use an implicant that's not prime. Okay. All right. Now, once you've listed the prime implicants, you will often find that some of them are forced. And that's because they are the only implicant, a prime implicant, that covers a particular element, in which case you're going to have to use them. So here I have the pink one and the blue one are both forced. The pink one because it's the only one that covers cell 2, and the blue one because it's the only one that covers cell 5. The green one is not forced. Right? If you look at its cells, there's always a different choice for each of it. Okay, but it is prime. It itself is not in any other implicant. Its parts are, but not the whole thing. Okay, that's a very important distinction. Okay, so only the prime implicants are needed. The forced ones are absolutely necessary, so we include the forced ones. So after I include the forced ones, I'm done in this case. That covers everything, and so that is my minimal sum of products. Okay, I can't do better than that. Okay, so this is a procedure. Draw the K-map, fill in the onset, fill in the offset. Be careful how you label the K-map. Step 2, list all the prime implicants, not the implicants, the prime implicants. Okay, you cannot decide that you want to leave one out, even if you can see ahead, or if you have ESP and you know you won't use it. You need to follow the procedure, because I'm not interested in the right answer. I'm interested in how you got there. Okay, you are in fact proving that you have the minimal expression by following these steps. Okay, so you need to list all the prime implicants. And then once you've done that, you see which ones are forced. You include all the forced ones in step 4, and then you may be done, or you might need to pick a few more. And then you need to make an argument as to why the ones you picked are going to be best choice. Usually at that point, it's a small enough problem that it's easy to give a simple argument. Okay. All right, so I think we did 3 of these. Yeah?
Do you just have maybe an example of what that argument would look like? Are there common reasons for why you would?
Well, there might be one cell where you have 2 choices, and one implicant might be bigger than the other. Or they might be the same size, and then you have a tie. And it's possible you might have more than one minimal sum of products expression. On the solutions in the homework, I will list all of the minimal because I don't want the grader to mark you wrong if you picked a different one. Okay, so when there are several possible minimal expressions, you only have to come up with one of them. Okay, but the solutions will have all of them. Yeah?
Should this argument be like a complete sentence or a bullet point, or?
It doesn't need to be very involved. You can just indicate which ones are the best choice for the homework.
Just for assignment purposes, a sentence?
Yes, a sentence. Go ahead, put a sentence.
Thank you.
All right. So we did this one, right? So I'm not going to repeat these. You can go look at the video or the slides. We did this one. Yeah.
So I noticed that sometimes we're looking for max terms and sometimes we're looking for sums of min terms.
No. We're always looking for sum of min terms or product terms here.
So the capital M versus lowercase m doesn't matter.
Oh, okay. So this is how the function is specified. How I tell you about the function, that could be in any way. I could tell you that the cells that start with the letter T should have 1s in them. Okay, that's kind of a strange function. So you would put a 1 in 2, 3, that's it. right? So how you're given the function to minimize could be by specifying where the zeros go or where the ones go. Right? If you know where the zeros go, you know where the ones go, and vice versa. That will not be true in about 15 minutes, but for now. Okay, so but once you filled in the K-map, it doesn't matter how you got there. Yeah.
The final function is always going to be an SOP.
Well, if you ask for a minimal SOP, it's going to be an SOP, yes. Okay, so this one we came up with had 5 literals. They were all forced, so that was pretty easy. Then we did this one where 3 of them were forced. Even one that was a 2x1, even though we had a lot of 2x2s. And then we needed to choose one here, right? So the ones that were forced are shaded. And after we picked the forced ones, we had 3 cells that needed to be covered. And of course, there is one and only one PI that covered all 3, so that was the best choice. So you might say this, you say best choice because it's the only one that covers all 3. Okay, and then we did this one, and this one was a little more complicated. It only had 1 forced PI up here, and then we had a bunch of 2x1s. And after taking the forced ones, we had 4 cells that we still needed to cover. And then we made, again, a simple argument. I need 2 2x1s to do it, and I can do it with 2 2x1s. So that's the best that can be done. Okay, all right. And then we had one more that we didn't get to. So let's do that one right now. Uh-oh. Aha, okay. So this time I will be sure to label my K-map to begin with. Okay, I need a colored pen. We'll use green. Okay, all right, so this time we were given the offset, right? So we know that there's a 0 in 0, 1, 4, 6, 8, 9, 12. So that's 7 zeros. Okay, so there's a 1 in 2, 3, 5, 7, 10, 11, 13, 14, and 15. Okay, and you see any PIs here? Yes.
5, 7, 13, and 15.
Okay, there's a nice 2x2 here. And what's the product term? Yeah.
Sorry, I'm going to say 15, 11, 14.
Well, let me get the product term for this one first.
BD.
BD, okay. All right, which one did you want?
Sorry, 15, 11, 14, and 10.
Okay, so these 4. And what's the product term for this one?
CD. A CA.
Okay. All right, any others? Yes.
3, 7, 15, 11.
Okay, and what's that one?
CD.
CD, okay. Yeah? 3, 2, 11, 10. Okay. All right, so unfortunately nobody tried to draw just these 2x1s. Okay, so this is an easy mistake to make, is to forget that the left side is next to the right side as well as the top and the bottom. Okay? And what's this one? What's the product term? B not C. Okay. Any more? No? Yes?
Isn't it supposed to be C, not B?
No, it's B not C.
Oh, never mind.
Right? We're in C and we're outside of B. Okay. Any more? Okay, so this is a danger point. Stop. Count to 5 and make sure you didn't miss one. Okay. All right. Are any of these forced? Yes. Okay, which ones? Okay, so BD is forced because of 5 and 13. Forced, okay. AC because 14. Because of 2, right? Okay. All right, so my sum of products is going to have BD, it's going to have AC, and it's going to have B bar C, which means that I have covered this, and this. I don't need to cover anything else, right? That's it. So I don't need to take CD. Number of literals is 6. Okay. All right. So that's our sum of products. Okay, now it's equal time. What about product of sums? How do we do product of sums? How many of you have done K-maps before and have done product of sums? You may have learned a different method, and that's fine if you can do it correctly, no problem. But I find that people sometimes make mistakes when they have two different ways of figuring out the product terms and sum terms. So the way that I suggest you do it, or if you're not comfortable already doing it another way, is to reuse the procedure that you will have already learned. And this avoids a lot of issues and mistakes. Okay, so the idea here is that to find a product of sums expression, what we're going to do is find a product of sums. We're going to look for a sum of products for the complement of the function. And then at the end, we're going to apply De Morgan's law because we want something for the original function. And when you take the complement of a sum of products, you get a product of sums. Okay. So here's the idea. This is the same function we had before, same example. But now I'm going to find the prime implicants of f prime, or f bar, which means that I'm going to suspend belief and think of zeros as ones and ones as zeros. So when I go to draw my rectangles now, I'm going to cover the zeros. So it's the same exact technique, only now I'm covering the offset instead of the ones. Okay, and there are in fact 3 2x1s here when I cover the zeros. And the product terms that correspond to these are obtained the exact same way as you did before. So this green one is not in A and not in B and straddles C, so it's A bar, B bar. And this one is not in B and not in C, so it's B bar, C bar. And the blue one is not in A, but it is in the C's region, so it's A bar, C. Okay? Which ones are forced?
Not B, not C.
Okay.
Not A, C.
Okay. Basically the same two colors, right? The green one is not forced. Okay, so now we're doing it exactly the same way that we did before. Okay, and now I'm for my cover. I take the two forced ones. Have I covered all the zeros? Yes. Okay. All right, but now we're not done. We have one more step because remember I wanted the original function. I don't want a sum of products for f bar. I want a product of sums for f. And the way I do that is, well, if f is f complemented twice, so if this is my product, if this is my sum of products for f bar, then I'm going to complement it. And then when you distribute De Morgan's law, this is going to turn into a product of sums. Okay, so I know some of you may have learned how to cover zeros and get some terms directly, but this often leads to confusion, and the complementation of the individual variables is reversed when you do that, and it's easy to get confused. Here you're learning one procedure. You just apply it to the zeros, and then you have this extra step at the end. Okay, all right. So I guess we should do one of these. Okay, so I think this is we did this one. We did the sum of products for this one, right? So, which time? Where do my ones go? Okay, x, y, z, w. So this is 0, 4, 8, 10, 11, 12, 13, and 15. So 0, 0. So this is the same K-map that we did before. But now I'm going to circle the zeros. Okay. Do you see any prime implicants of f bar? Yes.
0, 4, 12, 8.
0, 4. No, we're f bar.
Oh.
Right? So now we're covering the zeros. 1, 5, 3, 7. Okay, so what product term do I get for that? Okay, so this one is outside of x, it's in w, it straddles z, and it straddles y. Okay. The one below, okay. What's this one? Okay, any, yes?
9, 1.
9 and 1, okay. And what's that one?
W, not Y, not Z.
W, not Y, not Z. Which one? 6 and 14, okay. Okay, is that it? More? Okay, which ones are fixed? Which ones are forced? Okay, so this one's forced. Okay, and this one's forced. And that one's forced. Oh, this is too easy. Okay. All right, so we have x bar w plus x bar z plus y bar z bar w plus y z w bar. Number of literals is 10. Okay. Should we do another one or not? Yes, what? I'm sorry? Oh, good point. All right, so this is F bar, right? Okay. So what is F then? Well, we could do the same steps I did here. Okay, or you can notice that each one of these is going to become a sum term, and you need to invert the complemented and the uncomplemented. So this is going to be x plus w bar, and this will be x plus z bar, and this will be y plus z bar plus w bar, and this will be y bar plus z bar plus w. Okay. All right, number of literals didn't change, right? Doing this does not change the number of literals in your expression. Okay, did I mess up? Yeah. Why?
Yeah, there should be a Z bar in the sum of products, and then no bar.
Okay. Okay. Do you want to do another one, or should we go on? Yes. It's still wrong.
Yeah, that's the wrong
The
one.
third one needed the
Right.
That's the one right next to it, is the one up.
You mean, oh, I corrected the wrong one. Urgh. Okay. All right. Should we do another one? Yes? No? How many people want to do another one? How many people don't want to do another one? No, I think the ones, okay, we'll do one more. Okay. Or you want to work on it first? Okay. I will do it secretly over here. And then we'll compare. Wait, I guess I got to put it back for you. Or, wait. It's that one, okay. So you have it there, okay. Oh, I did it again. Oh, shoot. All right, ready? Everybody ready? Yes? Anybody want more time? No? Okay. So what did you get? Did you get this? Yes? Okay, I got it right. Okay, and to finish it off, number of literals is 7. Okay. So how did that compare? We did this one, right? So when we did the sum of products for this one, we got 6. Yes? Sure. No, right. I think it actually asks you, right?
Yeah, you have to.
I think the question asks for number of literals. You did not read. This is not a good idea not to read instructions. It generally helps. In particular, it makes a big point that you have to list all the prime implicants. We're not interested. If this is your answer, you will get 0 points. We need the K-map. We need the list of prime implicants. We need which ones are forced. Okay? Yes?
Will we lose points if we're sort of skipping steps of the process in problems where finding the SOP or POS form is not the focus of the problem?
Probably less points. If there's a K-map problem and we specifically ask you to come up with a minimal sum of products, we need to follow the procedure.
Well, yes.
If you're generating logic and you want to get minimal expressions, that won't, that's not so much the focus. You won't get docked for that.
Okay, so it's good practice and required on problems where it's the point of the problem?
Well, we're asking you. I actually don't leave it to your judgment. I say, show me all the prime implicants and identify which ones are forced.
Yeah.
Okay, all right. Okay, so we can do both product of sums and sum of products. Do you think one of them is going to be better than the other? Do you think sum of products would generally have fewer literals? How about product of sums? No. Okay, so for each function where the product of sums is better, there's another function where the sum of products is better, and that's its complement. So, sometimes one will be better than the other, but in general, there's not one that will always or most of the time be better. Okay, don't cares. Okay, apathy. All right, so sometimes there may be input values that don't matter to you. And here's an example of how that could happen. Suppose you are building an adder for 2 3-bit vectors. Okay, no carry-in. Okay, so there's absolutely no carry-in here. And you want to display the 4-bit results on a digit of the hex 7 segment. Well, if you look at this sum value here, what's the largest value it could take on? 4? What, 15? Can I get to 15 by adding 2 3-bit numbers? What's the largest 3-bit number? 7. So if I add 7 and 7, does that get me to 15? 14. So because I don't have a carry-in, I can't generate 15. If I had the carry-in, yes, but I don't. Right? So the value here is going to range from 0 to 14. So when I make my hex 7 seg, I can take advantage that 15 is a don't care. I am guaranteed that in this case, 15, for this particular application, 15 will not occur as an input. Now, is this a good idea to do this in general? No, because I want to use my hex 7 segment for something else, then 15 might not give me the right value. Yes? Do you have a question? Yeah, these are unsigned, yeah. They're just a plain adder. No subtraction, no net, right? Okay. All right, so I am now going to do the logic for this hex 7 seg, taking advantage of the fact that 15 is not going to occur, which means that when I come up with the logic for hex 7 seg, I could decide what the output for 15 should be. I can make it 0, or I can make it 1. Okay, so let's look at the, when you did the hex 7 seg, you had to come up with a function for each one of these segments. So if we look at the top segment here, remember this is going to be on for when you display 0. It's going to be off for 1. It's going to be on for 2, on for 3. It's going to be off for 4, on for 5, 6, 7, on for 8, 9, on for A, off for B, on for C, off for D, and on for E, right? Because these are active low, right? You all did this, so you should be very familiar to you. Okay, and now in cell 15, I have a question mark. I have two choices. I could decide that's a 0 there, or that's a 1 there. And what I want to do is decide which one gives me the better logic, the smaller logic function. So there's two cases. Suppose I make it a 0. Okay, then 15 is a 0. Or I could make it a 1. Okay. Now, when I go to get the sum of products, well, all right, I told you which one was better. But why is this better? How many literals for this sum of products expression? 16, right? Because each one of these is four literals. They're min-terms. You're going to have all 4 variables in there. So now I have 4 of them, so that's 16. How about here? So 4 plus 4, and then these will have 3 each, so that's 14. Okay, so this gives me a better expression. So for the top segment, I should make it a 1. Okay, what about some other segments? So let's look at the C segment. Okay, and so I filled in the places where C is supposed to be off. And that's for 2, C, and E. And again, I have 2 choices. In this case, if I make it, I can make it a 0, then I get 2 product terms. And if I make it a 1, I get 3 product terms. So in this case, it's better to make it a 0. Okay? So when we do our procedure to get our expressions, we have to consider both cases. We can decide that the don't cares are 0s, or we can decide that they're 1s. And so what does that do to our procedure? Okay, so this is our new procedure for sum of products with don't cares. Fill in the onset, the offset, and now we have a third set. So some of the inputs or some of the cells could have question marks, which means that we get to decide. Okay. We now, again, need to list all prime implicants, but we will, for this purpose, we will treat the question marks, so don't cares, as 1s. So when we draw our rectangles, we will cover them, and we will draw the largest possible rectangles, pretending that they are 1s. The only thing that we don't draw is a rectangle that covers only don't cares. because we'll never use that. Okay, so what we're doing is we're using these don't cares to make our rectangles bigger, if possible. And when we make them bigger, our product term shrinks. Okay. Now for step 3, we're going to do the opposite. I don't have to cover the don't cares. So I'm only going to say a PI is forced if it covers an actual 1. So if a PI is the only PI that covers a don't care, that doesn't make it forced. Only ones, only actual onset elements can force a PI. Because I don't have to cover the don't cares. Okay. And then again we have the last step where the cleanup phase, where if there's something that we haven't covered in the onset, then we need to pick the smallest choice for that. Okay, and I have an example. Okay. Well, this is my don't care. Did I not? Uh-oh. That I bought. Oh no. Uh-oh. All right, well, we'll just do some of the products. That was easy. All right, and then we'll do the other one freehand. Okay, so sum of minterms. So this is my onset. This is my don't care set. And then the offset is everything else. Okay, so A, B, C, D. So 0, 1, 3, 7, 8, 10. And then I have don't cares in 6, 9, 14. 6, 9, and 14. So if you go online, you may see that some people use D's for don't cares instead of question marks. Be careful. When you're working quickly, sometimes D's tend to look like zeros. Okay, all right. So let's see. Offset, I have 2, 4, 5, 11, 12, 13, and 15. Okay, anybody see any PIs? Yes. 0, 1, 8, and 9. Okay. And that is
C bar is B bar.
okay. Any others? Yes. 8 and 10. Okay. And that is
A, B bar, C bar.
okay. 3 and 7. Okay. Seven and 6. Okay. C, right? Okay, if it's you should, by the size you should kind of know how many literals it has, right? If it's a 1 by 1, it's a minterm, it'll have all 4 literals. If it's a 2 by 1, you lose one variable, so it'll have 3 literals. If it's a 2 by 2 or a 4 by 1, it'll have 2 literals. And if you're lucky enough to have a 2 by 4, you'll have only 1 literal. Okay, anything else here? 1 and 3, okay.
Which is A bar, B bar, B.
Okay. Any others? No. 10, 14. Oh, that's a good catch. Yes, that one. And that is?
D bar.
Okay. Any others? Yeah.
6 and 14.
Okay, so we don't want to draw that one because it only covers don't cares. So that's the only place that we deviate from the rule. Okay, so we're not going to draw the one that covers these two don't cares. Okay, anything else? No, no. Okay, so which ones are forced? There's this one, which is B bar, C bar, right? So this one's forced. Any other cells only covered by one? Oh, no. Okay, so this is the only forced one here. Every other cell has two choices, except for don't cares, but don't cares don't force anything. Okay, so we have B bar, C bar, plus, okay, so when I take B bar, C bar, I've covered these 4 cells, and now I need to cover these 2 and this one. Okay. This one? Okay, so if I don't take this one here, right? If I don't take this one here, then I'm going to need 2 separate ones, right? So clearly this is a best choice. So this is A bar CD. So this is a best choice. Hello. Okay. What about to cover this one?
Do 14 and 10 or 10 and 8.
So I could pick either one of these, right? So I could take A bar, B bar, D bar, which is this one, or I could take A, C, D bar. Okay, so, what's that? Choose either. So again, now I have a tie. So I have, this is a case where I will have 2 minimal expressions. So I need A bar, C, D, but then I could take A, B bar, D bar, or I could take A, C, D bar. Okay, so this is 2 minimal expressions. Okay. All right, we don't have time to do the product of sums. One of the things that you need to pay attention to is that when you do don't cares, the minimal sum of products and the minimal product of sums may not be equivalent to each other because you might have resolved the don't cares differently. Okay, I'll see you Friday.